Alright, today we're going to talk about covalent bonds. Alright, so we've talked about ionic bonds. Ionic bonds are when you've got two atoms, and let's say that you've got an atom like sodium. And sodium has one valence electron. So sodium's got this one extra electron, one valence electron. And so what happens is it wants to get rid of that one electron to get stable. So like chlorine, on the other hand, chlorine has 7 valence electrons already. So what happens, sodium gives away that one electron and becomes positive. Chlorine gains that one electron. Chlorine picks up that negative charge, then you have your case of opposites attract. Now that is ionic bonding. What we're looking at today is covalent bonds. Covalent bonds where two atoms actually share the electrons is all that happens. So you actually have a sharing of the electrons. That needs to be, it's not many multiple choice in this unit, but that's definitely going to be one. The electrons are shared. Now there's this little thing called Lewis symbols, but we're actually not going to look at that in this video. Matter of fact, because we're not even going to need it with hardly anything this year in 10th grade. But next year in 11th grade we'll do a whole unit on this kind of stuff. What I want to do first is, how do you know it's a covalent bond? We need to do that first. So how do you know it's a covalent? Well, first let's go back to this. How do you know that it's an ionic bond? What did I teach you to do to distinguish that it's an ionic bond? Well, if you remember, I said to look at the zigzag on your periodic table. If you see anything to the left of that zigzag, that means it is a metal. If it is a metal, then it's going to take place in an ionic bond. So that's it. So in theory, an ionic bond, specifically an ionic, occurs between a metal and a nonmetal. So there's your ionic bond. So how do you know it's covalent? Well, a covalent bond is when it's nothing but nonmetals. So over to the left, you got your nonmetals. And so any bond that takes place over here, these are all going to be covalent. So say, for example, N and O are both to the right of that zigzag. Nothing is over here. That's going to make this a covalent bond. Maybe F and Cl. Well, same situation. Anything to the right of this zigzag over here. Now, there's actually more to it than that, but we'll worry about that later. Hydrogen actually gets involved in a bunch of sharing, but we've talked before about how hydrogen doesn't really fit in with these metals. So that's why hydrogen will still show up in a lot of covalent bonds. So nothing strange about that. That's why some periodic tables actually lift hydrogen off the periodic table, I guess, just to show it does have some differences from these common metals over here. So now, let's kind of go back to the notes. So take a look at these first examples I'm doing. I'm going to work them on the bigger paper so they're a little bit larger. But anyway, N2O, NO, look at them. N2O3, NO2, and N2O5. 5 different combinations of N and O. But how do I know that this is covalent? Because the N is to the right of the zigzag and my O is to the right of the zigzag. So I know that this is going to end up being a covalent bond. And for somebody who's watching this and they're like, oh, there's example. Well, watch the videos on chemistry and I'll teach you further ways of telling. This is intended for the 10th grade audience. So here's what I'm going to do. Here's the ones that I've got written down. I'm supposed to be working out at this time. N2O. NO is the second one. N2O3. NO2. And then the next one I've got is N2O5. So there's my 5. So look, 5 different combinations of N and O. Now you'll notice in the notes, I've got 2 ways of naming this. A stock method and a traditional method. Believe it or not, you already know the stock method. The stock method is how we end up using our Roman numerals. So here's what we're going to do. Using the stock method to name these. So using the stock method. Stock method just means Roman numerals. And that's a neat thing. If you wanted to, you could still use Roman numerals to name these. For example, this one would be nitrogen, Roman numeral something, oxide over here. Nitrogen, Roman numeral something. Well, for that matter, this one is also going to be nitrogen, Roman numeral something oxide. Well, good grief. For that sake, every one of these would be nitrogen. I can just sit here and go down the list. Nitrogen, nitrogen, nitrogen. Every one of these as I go down. And these are all going to be Roman numeral something and oxide on the other side. Oxide and oxide. So let's go back and see if we can't figure out the Roman numerals that go with these. Well, let's take a look. O is a -2. So let's do this. You know how to do this game already. O is a -2. Which means, now look at this 2 that's here. Why did somebody put that 2 there? Well, remember, the sum of your oxidations has to be equal to 0. So if somebody put a 2 there, and that's a -2, what is this N? Well, this N would have to be a +1, right? Because that would give you 2 minus 2, that's 0. So this is nitrogen 1 oxide. Well, that's neat. The next one, O, this is what's neat. O is going to be -2 all the way down the page. They're all -2s. So let's go back to this. If O is -2, and this N, and notice how it's balanced out, this must be a +2. Roman numeral 2. What about this one? What do you do? And it's 3N2. What do you do? Look at this. -2, and somebody put a 3 there. Well, this is 3, and that's 2. Why did they do that? To get to 6. So this means this one should be 2 and, how you get to 6? What do you do when it's 3N2? There you go. I'll put my 3 right down there. Take a look at the next one. 2 and -2. Why did somebody do this? If there's a 2 there, and that's a -2, what did the N have to be? Obviously, it had to be a Roman numeral 4. And then the last one, check this one out. 5 and -2. Well, that makes a 10. So that means this had to be 2 and +5. So Roman numeral V. Now, this is what's neat. Okay, I want you to watch me what I'm about to do. This is the stock method. Stock method. That's what I can do to the stock method in terms of doing this. So now I want to go back and I want to redo those. And I want to do them this time using the traditional method. So N2O, NO, N2O3, NO2, and N2O5. Now, we're going to come back and we're going to name these what we call in the traditional way. So we're going to name these in the traditional way. Again, the only reason we get to do this is because N and O are both to the right. So, for that matter, we can do the traditional way. So what does the traditional way mean? Well, you're going to have to write something down. If this is the traditional way, it means we get to use a little numbering system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We get to number all the way to 10. 1 is mon. 2 is di. 3 means tri. 4 means tetra. 5 means penta. Hexa. Hepta. Where am I at? Penta, hexa, hepta. What are you thinking next? Ocho? No, I'm sorry. That would be the wrong class. This would be octa, nona, and deca. So, there, what we call these are known as prefixes. So we get to use these prefixes that you're looking at, but we only get to use these if it is covalent, which means if it's covalent, everything is to the right of the zigzag in the question. If you look at a problem and you see a metal then you can just get rid of this. This stuff is going to do you no good in the question. So, here we go. Covalent bonds is what we're looking at. So now, I want to go back, and you already know these. You just don't know that you know them. The first one, I've got 2 N's. Well, the prefix for 2 is di. So that means that the answer to this one is dinitrogen. And then I've got 1 oxygen. So that's 1 oxygen. So I get called this dinitrogen monoxide. Do you notice something I got to do? And this is very hard for me, because remember, I am a plus and minus kind of guy. But notice, when I do the traditional method, I don't even have to do the pluses and the minuses. Take a look at the next one, N and O. Now there's 1 N, and I know you feel compelled, shouldn't we say monotrogen? No, it just sounds weird. So I'm just going to say nitrogen, and then 1 O, I'll write monoxide down beside it. That's how you do that. About the only time you use the mon prefix is when it's on like this, on the end of the problem. I've never written monotrogen monoxide before. I've never done that. It'd be like saying carbon monoxide. It doesn't work that way. The next one, 2 N's and 3 O's. So I've got a dinitrogen, and I've got a tri, and then oxide. Oh, I get a little camera shaky there. Next one, I've got 1 N, but I don't say monotrogen. I just say nitrogen. So this one would be nitrogen. 2 O's would be dioxide. And once again, look, I'm not doing any pluses and minuses with these. N2O5 would be dinitrogen. And pentaoxide, all one word written out. I just got a little gap in mine by accident. So that's what these problems look like. No pluses and minuses. Traditional, but again, we can only do this traditional mon-di-tri if it's covalent. If it's ionic, wad that up, throw it in the trash can. It's not going to do us any good. Alright, now it's your turn. Let's see if y'all can do a few of these. CO2, you've heard of that one plenty of times. And you've sure never heard mon-carbon. So what is CO2? Ooh, it's what? Carbon. And then we're going to chase that with dioxide. Very good. So there's carbon dioxide. Next one, CO, which is deadly. Carbon monoxide. What about PS2? Well, P is phosphorus. Phosphorus. And I always misspell phosphorus. Even I do. And that's one y'all misspell. So take a look at the name so that you get it right. Phosphorus. Phosphorus disulfide. I'm going to leave off the CF2CL2. It's actually an organic name is what would give it. So now a lot of people mess up SO4. They see SO4 and they go sulfate. No, SO4 is called sulfate. We would call it sulfate if we saw like NaSO4, then we'd say sulfate. This is just SO4, no plus, no minus, all sitting on its own. So SO4 we would call sulfur, and then we would go tetraoxide. What about CO3? Yes, that's known as carbonate, but this is not carbonate. This is just CO3 all by itself. Carbon. What would 3 O's be? Trioxide. Now, I love doing these questions. I love, especially when we get the opposite. Say you're looking at a sheet of paper, and you've got, say on the paper says nitrogen, and I'm just going to make something up. Nitrogen, difluoride. Is there even such a thing? I don't know. But I do know this. Nitrogen is an N. Difluoride means NF2. And that's the answer. Notice how, when you're doing covalence, you don't need your pluses or your minuses. And it's very hard for me to say that because I am a plus and minus kind of guy. Whew, just marked my finger. Kind of hurt a little. Anyway. Well, so from now on, when you do a problem, the first thing you're going to have to do when you get ready to name it is you're going to have to take a look and go, is this ionic or covalent? So, say for example, let's say that I gave you potassium. Let's go with potassium oxide. Now, when you get ready to do one like potassium oxide, you're going to have to go through, look up K. K is a +1. Oxide is O, and it's a -2. And now you've got to know to come back and put your 2 in here to make this problem balance. Well, I mean, now this gets to be really great. What if you saw silicon dioxide? Soon as I see the di in this, I'm going to be like, I don't even need a plus and minus. I can write silicon dioxide means O2. And notice, no pluses, no minuses are even involved in this. What about, let's see if I can throw something else at you. What about if we had Fe, let's go with Fe2S3. Is that ionic or covalent? Well, Fe is to the left side of the zigzag. That means this is ionic. So, since this is to the left of the zigzag, do I even get to use any of this? No, I don't even get to use it. So, I'm just going to go iron, but this is iron, so do I need a Roman numeral with it? Whenever I do ionic, I always got to check for this. Iron has more than one oxidation number, either 3 or number 2. So for me, I'm going to have to figure out what Roman numeral this iron is. Sulfur becomes sulfide, and now I got to go back and look. S is a -2. So look at what somebody's done. 3 and 2, 2. What has this got to be? This has got to be iron. I know it's a plus. It's got to be iron +3 is my answer. That's how we end up having to kind of go through and take a look at this. What if I saw this on the paper? PS2. Hey, I still got PS2. Never mind. Wrong subject. What if you see PS2? Well, is this ionic or is this covalent? Well, let's see. P is to the right of the zigzag. S is to the right of the zigzag. If everything is over in here, that means this is covalent. Uh-oh. If this is covalent, I can use this sheet of paper. I can use my prefixes. So since this is covalent, I've got 1 phosphorus. Don't say monphosphorus. Just say phosphorus. And then 2 sulfurs means disulfide. Alright. Good luck, happy hunting, and all that other good stuff that goes along with saying good luck. But anyway, bye y'all.